Hello, everyone. Thank you for attending my PhD defense. Um, my name is Nick Kroeger, and I'm happy to present a two-pronged approach for improving machine learning interpretability. All right, so at a high level, what is AI? AI or machine learning enables computers to basically learn or make predictions without being explicitly programmed. And these models can handle various types of inputs, such as tabular data, images, speech, and text. And as AI evolves, so does our interaction with it, affecting not just the end users, but also professionals such as doctors who use AI that actually influence their decisions. So it's crucial for these models to be accurate, robust, and fair, among many other important qualities, to ensure that they work well and fairly for everyone involved. Deep learning and artificial neural networks are also at the forefront of AI, consistently delivering top-tier accuracy in numerous fields. And these models are central to many applications that impact our daily lives, whether it's driving assistance through autonomous vehicles or making personalized recommendations. So this is a subset of applications and highlights a widespread integration of AI in modern society. So today I'm talking about interpretability or explainable AI. So what is it? Um, Despite their superior performance of deep neural networks, they often lack transparency. And so an XAI, a black box, is a model that's deemed far too complex for humans to understand its reasoning. In general, the larger the model, the more obscure the decision-making process. And this lack of transparency can lead to unintended consequences, such as harmful biases or erroneous decision-making in high-stakes domains. XAI aims to make these advanced models understandable and trustworthy, ensuring that they can be validated by humans. So we note that explainability is the ability to provide insight into a model's behavior and is often interchangeable with the words interpretability throughout the XAI literature. So XAI, like AI, is not always necessary. However, there are some instances when it is required. It may be required by law in some situations to ensure decisions made by AI are fair and transparent. When AI decisions have serious consequences, understanding the why behind decisions becomes crucial. Plus, when we're dealing with new or untested problems, XAI helps build trust, making sure that these systems are not just black boxes. On the other hand, XAI may be desired simply for debugging models, monitoring them, communicating decisions to certain audiences, and conducting thorough audits on AI. All right, so this brings us to our first approach for improving interpretability. This work explores whether in-context learning can help large language models explain the behavior of other complex predictive models. This work is a collaboration with Hima Lakkaraju's lab at Harvard, where I spent a summer in Boston. And this is the first study to explore the potential of using LLMs as post-hoc explainers. So it was funny when Hima first told me the idea of using large black box model to explain other black box models, which is the core of this idea. I thought it was crazy, but it was actually a crazy idea that just happened to work. So here we use in-context learning for our approach. In-context learning is a prompting method that basically will allow an LLM to perform well on new tasks with only a few task samples in the prompt. And in this work, we propose a novel framework called in-context explainers. And this comprises two broad in-context learning strategies, such as perturbation-based and explanation-based ICL. These prompts are used to explain tabular and text classifiers, as well as logistic regression, vanilla neural networks, and transformers. And finally, we evaluate our method using faithfulness metrics such as feature agreement, rank agreement, and prediction gap. All right, so let's look at a brief overview of the proposed methodology. Given a data set and a model to explain, we create a prompt with a set of ICL samples. And to explain a single instance from a black box model, given the inputs and outputs, we format the prompt with context. So what is the context of the problem? What's the ICL subset? What is the task question and instructions? We then ask the LLM to identify the top 5 features driving the model's output based on the ICL set. This prompt is then fed to a large language model. And the LLM then returns a reply with its reasoning, and the answer is formatted on the last line in comma-separated format. A script then parses these replies and calculates our faithfulness metrics. So I go into results and methodology in a lot more detail in the dissertation, but here for this presentation, I'm just giving a high-level overview of the method so that I can really focus more on the cluster paths method, which was really a central part of the proposal. So in summary, this LLM explainer generates post hoc natural language explanations. It's based solely on input-output pairs, and so far they've been tested on tabular and text data. And it's primarily for ranking feature importance without needing internal model access. Okay, so that's the LLM work. Now moving on, now I'll introduce cluster paths. So unlike in-context explainers, these generate explanations based on the model's internal feature space. So this research is motivated by the following question, which is, can we effectively summarize and trace neural network decisions? So now I'll go through an illustration motivating the idea of a cluster path. First of all, neural networks we know are black box models, but that doesn't mean that we can't gain insight into their decision making. So what that means is that we can actually analyze their internal representations, like hidden layers, look at outputs and learned patterns through interpretability methods. And these models are basically made up of layers of nodes where each layer transforms the data using a series of matrix multiplications. All right, so assume we have a trained neural network, and let's look at how this cat image is forward propagated. So from the input to output, we transform the image into a series of hidden layer features, and these layers nodes represent activation values. And so as we forward propagate here, ultimately we get a prediction at the output layer, and this prediction is given by the largest activation in the output. So now for ease of illustrating the concept of a cluster path, let's just map each individual node value to an arbitrary color scale. And now we can use this to easily find recurring patterns among nodes in this network. So to do that, similarly, let's see how this network might process this image of a dog. We can see completely different activation patterns emerging across input samples. And now let's focus in on just one layer, the first hidden layer, and let's try to find any commonalities among the input images. So take a second and see if you can actually spot any patterns among these layers activations. All right, so we can see one potential pattern of orange activations on top and blue on the bottom. Now, can you spot any patterns among these dog images? So we can see a potential pattern of green and then blue and then green again. So let's look at this first hidden layers activation side by side, and let's actually add in more pictures with their associated activations. And go ahead and take another second and see if you can identify any additional patterns. All right, so here is one of many ways to group these activations together. Looking at the images in each cluster, we can see what is common among them and what is unique between pairs of clusters. For example, we find that perhaps the first group of activations represents sleeping animals, and the second group represents a smiling concept, and the third group represents animals with a neutral gaze. So to illustrate the idea of a cluster path, let's just plot these activations down to 2 dimensions with their associated labels. And in this case, each color here represents a unique cluster, so different from before. We're just coloring clusters. So let's say that this image falls into the smiling cluster in layer 1. And let's repeat this activation grouping for each layer and see what clusters we find next. So the next layer finds concepts of beach, indoors, and grass, perhaps, and this image falls into the grass cluster. The long hair cluster in the next layer, and finally, the dog classification in the output layer. So we can now see the core idea of a cluster path if we traverse um, the clusters across layers in the network. So taking this further, if we assign labels to clusters, we can now create a concept path, which I'll talk about more later. But to reiterate, this is just a toy example demonstrating what a cluster path is, but it's not necessarily the true activation values or concepts that this made-up network has learned. So, however, the core idea still holds throughout our experiments. All right, so more concretely, what is a cluster path? So we've seen it's a simplified representation of how a sample propagates through a complex neural network and reaches a decision. It's represented as a sequence of cluster IDs, one per layer. And the goal here is to identify groupings to simplify the model's reasoning. All right, so what is the methodology? How do we do this? So cluster paths are made post hoc, meaning we are given a trained neural network and tasked with explaining it. And given a trained neural network, we forward propagate the training dataset and record the activations at each layer in the network. We then cluster each layer's activations, and using a clustering algorithm such as k-means or Gaussian mixture models, for example. And finally, we save the cluster centers at each layer, and then given a new sample, we can now enumerate the path through which the clusters have highest membership to in each layer. So that's generally the methodology and how it works. With this idea of a cluster path, we are now interested in answering key questions about them and the model's reasoning. So first, we ask, can cluster paths identify spurious cues? Can they faithfully represent the model's logic, or is it actually capturing something else altogether? What concepts did the model learn? And can we use cluster paths to identify model weaknesses, such as biases or representational drift? And finally, how can we scale cluster paths to large state-of-the-art vision transformer models? All right, so first we're going to look at what are spurious cues and why it's important to identify them. So take an example of a fish versus dog classifier, and say the dataset consists of fish underwater with blue backgrounds, and dogs not underwater and not with blue backgrounds. So it may be very easy for the neural network to achieve high accuracy, and you'll say, oh, this is awesome, my model is the best ever. But you may not know why, and this can lead to poor generalization and misclassifications if the new samples really differ from the training distribution. So perhaps one reason for the high accuracy could be that the network learned a shortcut such that if I see a blue background, that means fish, and if I don't see a blue background, that means dog. So in a more real-world example, saliency maps can reveal uh, when models focus on irrelevant cues. And in chest X-rays, some models predicted COVID-19 based on imaging artifacts rather than real pathology. And this highlights the need for careful validation to ensure that these medical models are truly diagnostic. All right, so now to test whether cluster paths can identify spurious cues, we first train a neural network on a modified CFAR10 dataset, which is just cats versus dogs, with intentionally injected spurious signals. So our spurious signal, we introduce a shortcut by adding colored patches. That's 90% of cats have red patches and 90% of dogs have blue. Our relatively small convolutional neural network consists of a series of standard 2D convolution, max pool, and ReLU functions, followed by a series of three fully connected layers. And the train and test set have this 90% correlation. And after we train the model, it achieves 95% accuracy on the test set. So, but that doesn't prove that it was trained on spurious signals, or that it picked up on that shortcut. So to prove that the model indeed relied on this, we create a corrupted test set that contains randomized patch colors for all samples, and we're therefore breaking that class to label rule. So we should expect a drop in the model's accuracy to random guessing. And we indeed see this is the case, confirming that the CNN has learned shortcut. So to create cluster paths here, the first conv layers of the model can be seen as feature extractors, and therefore throughout all experiments, we create cluster paths from the last fully connected layers where we're just analyzing the features learned in the network. Here we use k-means with k equals 2 clusters in all layers and 3 clusters in the final layer. We visualize the cluster paths as a subset of random samples, traversing the respective path, and we see that cluster path 0111 group together blue patched images, and 1000 group together red patched images. Lastly, we see 1002 group together all other patch colors that the model saw only 10% of the time during training. And quantitatively, well, we can see over 99% of samples in the first two paths have blue and red patches respectively, while the last path has an even mix of the rarer colors. So now let's compare our results to saliency methods. So we see strong attribution over the red and blue patches, highlighting exactly where the model is focusing in the image. For images with non-red or non-blue patches, the attribution shifts outside of the patch area, and this suggests that the model is no longer fixating on the spurious signal. And so this gives us even greater confidence that the model has learned a spurious correlation and points to the need for retraining. Comparing to other state-of-the-art, a related method is deep k-nearest neighbors, or deep KNN. And this compares test inputs to their nearest training examples at each layer, and it estimates confidence based on label consistency, such that a clean input shows stable labels, while adversarial ones show inconsistency across layers. Here's the results of deep KNN. This is a heat map showing average k nearest neighbor agreement by layer and by patch color. And so we can see red and blue patches have nearly 100% neighbor label agreement across layers. And this reveals again the model's strong reliance on spurious color cues. All right, so comparing all three methods, they all detect spurious cues a little differently. So cluster paths and deep KNN show what the model has learned, while gradient saliency shows where it focuses for classification. These methods all have differing memory requirements, and cluster paths are advantageous because they only need to store the cluster centroids, and it's on the order of L layers that you cluster, with K centroids per layer, and they're each d-dimensional. On the other hand, DeepKNN needs to store all layers activations on the order of n samples, which is not scalable for large data sets, for all L layers, each having H hash maps and d-dimensional vectors. Gradient saliency, on the other hand, only needs temporary storage, which is required for a single neural network backward pass. So each method has its limitations. Cluster paths involve a faithfulness versus complexity trade-off, which I'll talk about a lot more later. Deep KNN lacks interpretability tuning, and the paper really focuses on adversarial detection. Gradient saliency can be noisy or unstable due to vanishing gradients, and I'll discuss more on the limitations of cluster paths later. So when would I want to use this? Ideally, we'd use cluster paths to understand model decisions, especially in memory-constrained settings. So deep KNN is best suited for security-based tasks like adversarial detection with ample storage, and gradient saliency is good for quick checks. But not identifying cues with saliency there doesn't mean that those cues aren't present. So you have to be careful with that. All right, so that's the spurious cue experiment. And next we assess whether cluster paths truly reflect the model's behavior. So we're testing if the clusters are meaningful and explanations faithful to the model's decisions. So here we conducted experiments on the Celeb A dataset. It contains about 200,000 images with 40 labeled attributes. And we simplified the task to classify 5 hair types: gray, blonde, brown, black, and bald. So similar to the spurious CFAR cat-dog architecture that we just saw, the hair attribute CNN is a convolutional neural network, and it has a series of conv and max pool layers, followed by successively smaller fully connected layers towards the output. Since this model was trained in-house, it's good to know the accuracy, and here the model early stopped at epoch 14 with 90% train, 86% val, and 87% test accuracy. Looking at the confusion matrix, we can see confusions like gray versus bald or brown versus black hair are expected. And there's minimal overlap with classes such as blonde hair versus black hair. So to generate cluster paths, again, we focus only on clustering the last fully connected layers. And here we use k equals 5 clusters per layer, which matches the 5 classes. And while standard metrics like cluster validity metrics like silhouette score, Kolinsky-Haribaz, you could tune k, the number of clusters, but they really don't balance faithfulness and complexity, which is our main goal, which we explore next. Okay, so what is faithfulness? We measured decision alignment faithfulness, or DAF, to see how well cluster paths reflect the model's behavior. So to do this, we one-hot encode each cluster path IDs. We train a proxy model like random forest to predict the model's outputs and score it by the agreement. So here a higher DAF means faithful explanations. So we start with a really interesting faithfulness question, which is how much discriminative information is gained only in the intermediate layers? So that's layer 1, 2, and 3. So here this line plot shows how faithfulness changes as we increase the number of clusters in the output layer, which is the x-axis here. And setting only one cluster in the final layer, we can see a baseline faithfulness of 78%. And this shows that intermediate layers alone provide a substantial contribution into the model's decision making. So that's great that we're generating cluster paths from those layers. Increasing to 5 clusters in the final layer slightly improved the faithfulness score to 81%. Jumping to 10 clusters in the final layer yields 88% faithfulness. And using 15 in the final layer shows marginal gains in faithfulness at the expense of even more cluster paths to later analyze. All right, so another question that we look at with regards to faithfulness is how much of the model's decision boundaries are captured in the last layer alone with clustering. So with just 5 clusters in the last layer, the faithfulness is 71%. And using 10 clusters in the final layer, that raises the score to 88%. And as expected, this suggests that more granular, smaller clustering in the final layer will capture additional details of the decision boundaries, up to an extent in which you have a faithfulness plateau effect for increasing the number of clusters. So what are the takeaways of this experiment? Uh, our results demonstrate that the intermediate layers have significant contribution to the model's decision-making process. There is marginal faithfulness gains as we surpass 2C clusters in the final layer. And finally, clustering inherently abstracts away fine-grained decision boundaries. All right, so that's the faithfulness experiments. Next, we study how can cluster paths identify specific learned concepts or relevant features for classification with this Celeb A hair classifier that we created. All right, so there's a few case studies here. And in this first case study, we examined 3 cluster paths that the model predicts as blonde hair. First, cluster path 4002 groups images with medium to dark blonde hair and warm earth-toned backgrounds. Notably, some brown-haired individuals are misclassified as blonde, likely because they share similar background tones and gender presentation. In contrast, a very similar path, which differs only by one cluster here in the first layer, this is 3002, features cooler toned portraits, cooler meaning like colder, and often with whiter black backgrounds and lighter blonde shades. This path shows no misclassifications, but it's visually distinct from the first, suggesting that the model has learned different subtypes of the concept blonde. Then there is path 2242. So this is a small group of just 8 samples, half of which are misclassified, and all of them show women with very similar hairstyles and borderline blonde / light brown hair. So what do these findings suggest? They may suggest 2 things. One, that some errors or misclassifications stem from just labeling ambiguity rather than the model failure, since hair color is subjective and continuous. It may also suggest that the model likely relies on using background, lighting, or hairstyle, and not just the hair color which it was intended to train on, which are key features for classification. So let's do a similar qualitative analysis here for the gray hair cluster paths. Cluster path 2124 contains a mix of genders with several mixes of color tones such as yellow and pink. In contrast, we have a cluster path 1124, which consists entirely of men with dark gray hair and mostly wearing formal dress suits. We observe that there are no strong color filters overlaying these images in the path, as seen with its neighboring path 2124. So with the help of this cluster path analysis, we can see that the misclassified images in this path 1124 likely occurred because of the matching gender, dark gray hair, and a seemingly formal suit. So although this is arguably a mislabeled attribute in this LabA dataset by hair type, we can also argue that with this analysis, most individuals can easily recognize these patterns noted above, as they don't require any expert domain knowledge. Okay, so finally, in our last case study, we look at cluster path 1333, where most of the images are men with short dark hair wearing formal business suits. Interestingly, all 5 misclassified samples were labeled as black hair but predicted as brown hair. And 4 of these 5 also show men in suits, consistent with the overall pattern in this path. So this suggests that the model may be relying more on contextual cues like attire and hair shade rather than the label distinction between black and brown hair. All right, so let's compare these findings to gradient saliency maps. We can see for these 2 correct predictions here, the saliency maps all generally attend to the hair. However, for 2 mispredictions, we see that the saliency methods all generally ignore the hair and focus on other features such as the eyes, the forehead, and chin. And so, again, we see that saliency maps identify where the model focuses, but it does not have enough explanatory power to determine the overall learned concepts of the model like cluster paths can. All right, so that concludes the concept discovery experiment. And next, we move on to a robustness experiment where we measure to what degree are cluster paths robust to certain input perturbations, and what insight does that give us about the model? So to measure robustness, or more specifically, how stable the neural network's feature space is, we compare a sample's cluster path with that of its perturbed version. So for example, if this original image's cluster path is 1002, we perturb this image in several ways, for example, a saturation shift and rotation. The top perturbed image's cluster path is 1102. The bottom image's cluster path is 1232. And we can compare these image paths to the original and calculate a distance between them. So we calculate our novel path agreement score as the average path agreement across all n samples in the dataset. The path agreement A is parameterized by a discrete distance function d, and this calculates the similarity between path P and P prime. So one way we achieve this is by setting the function d to the Hamming distance, which is essentially the minimum number of substitutions required to change one path into the other. So for these 2 examples, we get an agreement score of 0.75 on top and 0.5 on the bottom. Okay, so to simulate these realistic perturbations, we run an ablation experiment, and we apply various combinations of mild geometric transformations, including rotations, 0 degrees, 5 degrees, and 10 degrees, translations up to 5% of the image's width and height, and scaling 0.9 to 1.1 times the original size. We evaluate the impact of transformations on cluster paths and the neural network's predicted accuracy. So averaged across 10,000 random test samples, here high PA or path agreement and accuracy indicate robustness to geometric transformations. So notably, this first row and first column in the table represent the original input without perturbation. First, we show the results for increasing translation and scaling without rotation. And we see that with an increasing magnitude of perturbation, both the path agreement and accuracy drop. The accuracy drops a maximum of 9% from mild to maximum perturbation, while the internal path agreement actually drops to a maximum of 22%. And as rotation magnitude increases, PA and accuracy continue to decrease in the same trend. So significant input changes can alter the feature space, while minor changes should maintain the original path if the model is highly robust. And larger perturbations might lead to different paths because of this threshold crossing in the cluster assignments. So the model indicates potentially weak generalization capabilities. So similarly, in this experiment, we increasingly add Gaussian noise in the images to study the effects on accuracy and cluster path agreement. Noise magnitude increases along the x-axis, with accuracy shown in red and path agreement in blue. And this pattern mirrors the previous results we saw, showing stable accuracy but a quicker drop in path agreement as the noise increases. Cluster paths therefore provide an earlier and more sensitive indicator of internal representational drift than output accuracy alone. So by monitoring this representational drift, potentially indicates a need for retraining, maybe with data augmentation, and practitioners can proactively detect and then address model brittleness well before any drop in accuracy is found during deployment. All right, so as neural networks become increasingly complex, it's also really important for us to address how can cluster paths scale to large models like vision transformers. Transformers were originally designed for text, but with the introduction of vision transformers, they've been adapted to image tasks and can now outperform state-of-the-art models like CNNs and ResNets. So, as a brief overview, vision transformers work by first splitting the image into patches. Then you flatten these patches to create low dimensional embeddings. Excuse me. Next, you add positional embeddings to retain that spatial information that you just broke. Then you forward propagate these features through transformer encoder blocks. And finally, add a multi-layer perceptron head to classify the features. So the model we seek to explain is a standard vision transformer, a VIT base with patches of size 16 by 16. And this classifier is trained on ImageNet, a large-scale dataset containing 1,000 classes. This transformer performs well, achieving a top 1 train accuracy of 93% and top 1 test accuracy of 85%. We next define cluster path. We next define a cluster path complexity metric, which measures the total possible number of cluster paths. So assume 20 clusters per layer. Creating cluster paths through all 13 of these layers would result in a mere upper bound of 81 quadrillion potential cluster paths. So it's a little too large for any one person or computer to analyze. So we therefore scale up our method by subsampling the layers equally spaced, and we assume 20 clusters per layer and 100 in the last layer. We get an upper bound of 800,000 paths. This is way better than the quadrillions before, but still way too many to analyze. Uh, However, thankfully, we find empirically that this is just an upper bound, and that we find that approximately 29,000 of the cluster paths are traversed by the dataset, and that's just a mere 3.6% of the expected cluster path complexity. So I'm not going to sit here and lie to you and say, oh yay, we got 29,000 cluster paths. That's easy. That's still a lot of cluster paths to analyze. So what do? We automate this task through divergence analysis with the help of a large language model. So this technique can allow us to identify core concepts that the model has learned. And we perform divergence analysis by basically keeping all clusters on the path fixed and changing only one layer of clusters at a time. So here's an example of what divergence analysis looks like applied to the VIT model. In this case, we fix the path suffix to 5774, and we modify only the last layer's clusters. So let's zoom in on some of these paths. We can immediately identify trends. The first path contains blue tones, the next path contains warm tones, and third path contains yellow-green items, the next blue, the next gray patterns, and so on. However, admittedly, this is subjective and also time consuming with human intervention alone. So let's call in our AI companion, GPT-4. In this case, we use it as a vision language model, or VLM. And this can actually enable us to identify those cluster concepts. Uh, what are those shared themes among them? So we actually give this image of the divergence analysis to the VLM and we prompt it, hey, identify unique themes within each path that is distinct from the other paths. Here's an example prompt template in which we provide background and detailed instructions of the task. So up until now, we focused on cluster paths that are solely a sequence of cluster IDs. But now we actually have the ability to replace those cluster IDs with identified concepts. And so this is really the core idea of a concept path that we illustrated earlier. Here are actual concepts extracted by the VLM, and we qualitatively validate that they align with human identified concepts within these paths. So after a series of automated divergence analyses, we can now fully enumerate the concept paths. And since each concept from the VLM can be as long as a short phrase, which can be pretty long, we apply NLP analysis, such as this will be a mouthful, term frequency inverse document frequency, or TF-IDF. And that's to basically narrow down the top three concepts per cluster. So for example, the top three concepts for cluster 18 in the first layer are forms or shapes or light. And the following concepts per layer are domestic or urban or contrast urban, then close or domestic or warm, and finally urban or transportation or community interactions. Another example concept path highlights these fishermen holding fish, and the concepts described are forms or shapes or light, texture or shapes or dark, human interaction or human, outdoor reflection or leisure or familial. So although there are some redundant or very broad level concepts here, we do recommend tuning the prompt for the VLM and NLP analysis as well per application or domain area. So with these results, we demonstrate that cluster paths can be applied to large-scale vision transformer models. In conclusion, cluster paths help reveal model shortcuts and biases by showing what features actually drive predictions. They offer faithful, concept-based explanations that reflect the model's real decision logic, not just surface-level patterns. They can also detect internal feature drift before accuracy drops, acting as an early warning system. And cluster paths can scale to large models like vision transformers, and are far more efficient and storage friendly than other methods like deep k-nearest neighbors. While powerful, they do come with trade-offs. Clustering in clustering high dimensional activations risk instability due to the curse of dimensionality, and the method assumes inputs are visually interpretable. It works best on deep architectures with multiple hidden layers, but an inherent faithfulness complexity trade-off will always remain a challenge. Clustering, as we've seen, also introduces some information loss. And looking ahead, a key research direction is deciding which layers, heads, or token positions to cluster, especially for transformers. So what are some of the strengths of cluster paths? Uh, Cluster path analysis is a powerful tool for model debugging. It helps us to uncover learned concepts and hidden biases. And this dissertation provides quantifiable measures of faithfulness, robustness, and path complexity. Additionally, cluster paths can currently be applied with any neural network that has a series of fully connected layers. With a tunable hyperparameter, you can balance the explanation, faithfulness, and complexity trade-off. And finally, their unique global perspective captures local group behavior as well as global trends in one view. Okay, so that is an overview of the cluster path experiments. And now we actually show two uses of cluster paths to show generalization. So first, rare paths actually signal out of distribution or OOD samples, and this helps flag risky inputs before misclassification can occur. Second, we apply cluster paths to segment coral reef soundscapes from terabytes of unlabeled hydrophone data. So I'll briefly cover OOD detection and then focus a lot more on the soundscape application. So OOD detection is the challenge is that basically neural networks are notorious for sometimes giving high confidence mispredictions. So we tackle this challenge of making neural networks more aware and helping them to know when they don't know. So our approach here is to compare a new sample's likelihood of being generated from an inlier set of cluster paths. So samples with similar features often share cluster paths, and this is a property called path homogeneity. If a new input follows a rare or unseen path, it may indicate an outlier. And so unlike deep KNN, which checks label agreement among the neighbors, cluster paths will flag inputs based on path rarity. We quantitatively measure average inlier versus outlier distribution detection, and we use AUROC, AUPR, and FPR at a fixed 95% true positive rate across 3 inlier datasets and 9 distinct outlier datasets. So when looking at average FPR at 95% TPR across all methods and inlier datasets, we see paths perform the best at identifying outliers. The same findings hold for other metrics such as AUPR and AUROC. Okay, so I did say that was going to be brief and more details are in the dissertation, but moving on to our second application, we apply cluster paths to identify distinct soundscapes within coral reef ecosystems. So coral reefs produce diverse bioacoustic sounds due to their dense species interactions, and understanding these soundscapes can help us learn more about these fragile ecosystems and fish biology, especially in relation to environmental changes like temperature, sunlight, ocean salinity, or acidity. So first, what is a soundscape? A soundscape is basically a composition of several sound sources in any environment. And so here's an example soundscape from a busy city. Um, so hopefully this works, but before I play this, please make sure that your audio is turned up so you can hear it, and let me know if this audio doesn't come through. Yeah, okay, thanks. So we can hear people, sirens, cars, etc. Oops. Now, coral reefs are abundant with life and numerous types of sounds. These can include fish calls, fish eating coral, whale songs, invertebrate snaps, divers, boats, waves, bubbles, even, etc. And so here's a 21-second audio clip with its respective spectrogram. And this shows basically a low frequency range on the y-axis. This is 0 to 1 kilohertz, that contain most species sounds and interactions. Warmer colors here, the reds in the spectrum, indicate louder events for a given frequency, and conversely, cooler colors indicate quieter events. So I'll play the audio twice. The first time I want you to try to guess where the events are and what they might be. Um, so it will initially sound crackly, but this crackling is the normal ambient sound. And on top of it, you might be able to hear some fish calls as well as some other miscellaneous noises. So let's take a listen to what a coral reef soundscape might sound like. Okay, so thumbs up if you could hear that. Okay, thank you. All right, so here I've identified two distinct fish calls within the ovals. as well as some short thumping or tapping noises denoted by triangles. So try listening again, but with this legend in mind. Okay, so there you heard a purr fish call. Kind of sounds like a cat purring, and some of those taps. So with a very large abundance of data, manually labeling these sounds or events is subjective. It does require domain expertise and is costly in terms of time and money. So example events include feeding behaviors, mating, boat noise, scuba divers, or predator avoidance. So this work is sponsored by DARPA funding with lead PI Lauren Freeman, whom I've worked with since 2019, and collaborator Daniel Duane from NAVC, who I believe is actually in the call today. Our goal is to automatically identify bioacoustic soundscapes. So we use an unsupervised learning approach in tandem with cluster paths to basically enable this large-scale, label-free acoustic segmentation. So with this, we can also gain model insights and a refined soundscape structure. So let's look at what is the data set. It's collected off the coast of Hawaii from April to December 2020. And this curated dataset consists of 105,000 1-second unlabeled spectrograms. They each range 0 to 700 hertz, and they're sampled over the course of this 9-month period. So on the bottom here are example spectrograms from the dataset. Our approach consists of 3 phases. Phase 1 is pseudo label or weak label generation, since we don't have any labels, so we need to make some. Phase 2 consists of training a CNN on these pseudo labels. And phase 3 consists of analyzing the model with cluster paths. So phase 1 is as follows. Given this data set of 105,000 spectrogram samples, we calculate 18 acoustic features on each spectrogram, and these give a compressed representation of the dataset's most prominent characteristics. Next, we can cluster this data using a Gaussian mixture model with 50 components, also known as clusters. Then we prune away the smaller clusters and any samples with low cluster membership. This leaves us with higher confidence, 29 clusters. And these clusters are used as pseudo labels or weak labels to train a CNN. Some preliminary soundscapes are seen here, where cluster 1 represents ambient background noise, cluster 2 represents boat noise, and cluster 3 represents fish calls. In phase 2, we train the CNN. We treat the spectrograms as images and train a special CNN, which is well suited for the wide 17 by 350 input data, as opposed to typical square inputs for CNNs. We train the CNN on spectrograms, and we achieve 75% accuracy. And as baseline comparison, we train a logistic regression classifier on the 18 acoustic features we saw earlier with 67% accuracy. And this validation confusion matrix provides a better picture of the misclassifications. And manually inspecting them, we see that most of the confused classes actually show most errors between spectrally similar clusters. So this suggests that the pseudo labeling noise is actually now the dominant performance ceiling. Finally, let's analyze the model with cluster paths. So we cluster the last 4 layers and apply PCA to reduce the dimensionality of the first layer. Now, how do we know how many clusters to use per layer? So as we increase the number of clusters k, the faithfulness shown by the line in blue, it increases but levels off at around 75%, again demonstrating this plateau effect. However, as we increase k, we also increase the cluster path complexity omega, which is shown by the orange line, and therefore making the model harder to interpret. So we make this trade-off very explicit here with the objective j shown by the green line. Here we want to maximize faithfulness while minimizing complexity. And one way that we do this is rescale the complexity to 0 to 1 and then find the optimal cutoff. With this, we find the optimal k to be 22. So we enhance our path analysis of cluster paths uh, by visualizing them on what's called a parallel coordinates plot. And here the x-axis is showing layer ID, the y-axis is showing cluster ID, and the lines that you see, the width is proportional to the number of samples in that path. It's also showing high misclassification rates in red and lower in blue. So among all paths, this is among all paths with suffix xxx1. We zoom in on the cluster path suffix with the highest misclassification rate. And among all paths with suffix xx91, we again zoom in, and now we're left with a very targeted analysis of path x1591. So here we show what are the cluster paths with that common suffix, x1591. Here, column 1 on the left, it lists the cluster paths ID and misclassification rates. Column 2 shows the average time profiles with amplitude on the y-axis and time on the x-axis. And the rest here show sample spectrograms. Each path groups similar spectral profiles, useful for refining weakly labeled soundscapes. One simple feature learned by the model is loudness. We can see that the model has learned to distinguish loud soundscapes from quieter backgrounds with distinct fish calls. The final cluster path analysis we examine is paths ending in cluster 1. So again, focusing in on a few paths for analysis purposes, we can see that sharp spikes in the average time profile show that the model has actually learned when sounds occur, not just what they are. So this timing bias suggests an actionable next step, such as maybe retraining, using a circular time shift augmentation to basically reduce that over-reliance on the event timing. And while it's not inherently flawed that this occurs, this insight revealing time sensitivities would be hard to uncover without divergence analysis. All right, so wrapping up, in summary, our joint approach of combining unsupervised learning with cluster paths enable a large-scale, label-free acoustic segmentation, additional insights into the model, and a refined coral reef soundscape. Comparing our two-pronged approach to advancing neural network interpretability, we can characterize cluster paths in this taxonomy as post hoc mechanistic interpretability, and it's a method tested on vision-based neural networks. Cluster paths are shown to be useful for model debugging, identifying concepts, and improving robustness. So overall, this work focuses on enhancing black box interpretability through in-context learning and cluster path analysis. Ultimately, this gives us more insight into how models make decisions. And second, I show how cluster paths can help improve robustness by revealing internal fragility and detecting when the model starts to drift or rely on spurious cues. Finally, I've developed new explainability methods that are practical and scalable, making them suitable for real-world debugging and model auditing tasks. So, wrapping up, here are relevant explainable AI research papers and efforts. And I wanted to note that in 2022, I founded this international XAI online forum where I share research, events, jobs, and host talks from leading authors. So feel free to reach out if you'd like to join. And here are additional research papers I've worked on throughout my time at UF. Um, so I wanted to give some acknowledgments real quick. First and foremost, I want to acknowledge and thank my late advisor, Dr. Gator. This cluster path idea was actually heavily inspired and motivated by him. And thank you to my former lab members for helping me along the way, as well as the numerous undergrads that I've mentored. Thank you to Hima Lakaraju and Lauren Freeman, as well as my collaborators at Harvard and NAVC. This work really would not be possible without you all. And a huge thanks to my advisor, Dr. Ben Shadler, and my committee members here today, Dr. Harley, Dr. Rashidi, Dr. Grant, and finally, Dr. Zaire, who unfortunately couldn't attend today, but played a really big role earlier on in my PhD. So thank you. You've all been very instrumental in helping me refine my research over the years. And finally, thank you to my family for your never-ending love, encouragement, support that really carried me throughout several setbacks on this PhD journey. So here are some of our memories together. And I want to express my deepest gratitude to my partner, Nick Askarati. And yes, we have the same first name. for being one of my greatest supporters throughout my PhD and always inspiring me to grow and reminding me of what truly matters. So, your encouragement, patience, and unwavering belief in me has really made this journey possible. A huge thank you to all my friends I've made along the way. You make life so enjoyable, and I'm excited to go on so many more new adventures with you. And this absolutely does not capture everyone, but I'm truly grateful to all of you. And so, with that, thank you so much for listening to my presentation.